All right, so this is where we left off last time. We were about to start talking about ionic compounds. Okay, so when it comes to the sharing of electrons, bonds are formed by sharing electrons. When it comes to ionic compounds, the sharing is not so much sharing. The metals lose the electrons completely. The nonmetals gain the electrons completely. So the metal forms a positive ion. It's lost a negative charge, known as a cation. And the nonmetal forms a negative ion called an anion. So one way you might remember that is remember that cats are always happy. Okay. So you have a happy cation. It's always positive. And down here you have negative ani. Ani is always negative anion. I don't know. I couldn't really come up with anything for anion, so negative ani. That's what you got. All right. Now, so you react these things together. You take a spark, you expose them to radiation, whatever it takes. You get negative and positive ions, and of course, negative charges will attract one another. And what they'll do is they'll form these three-dimensional networks, okay, where every positive ion is surrounded by negative charges, and every negative charge, or every negative ion, is surrounded by positive ions. So it's just these three-dimensional networks of alternating charges. Okay. Everywhere the positive charge looks, it sees negative charges. Everywhere a negative charge looks, it sees positive charges. Okay. So these electrostatic forces, as they're called, are very strong, and they extend outward, sort of uniformly in all directions from each of these ions. And that explains the properties of ionic compounds. Okay, first off, the bonds are non-directional. That is to distinguish them from some of the other kinds of bonds you'll see. Non-directional because those electrostatic forces go out uniformly in all directions. There's no preferred direction for any of that. But they also have a high melting point and boiling point. Okay. So when you add heat, when you increase the temperature, you're increasing the random motion of every particle in the substance. Okay. So there's no sort of preferential direction to any of the motion. So in order to melt something, what happens is the particles are moving fast enough that the individual particles, look around them and say, okay, I have the option of staying here in the solid form where I'm happy being surrounded by all these other things, or I can move into a liquid where I'd be happy because I'd be free to move. And that's really difficult for an ionic compound because they are really, really, really happy being surrounded by negative or opposite charges. Whereas you put them in the liquid, they're not necessarily going to be surrounded by opposite charges in that way. They're going to be happy because they're moving, but they'll also be bumping into same charges. So you have to put in a lot of heat. You have to increase the temperature a lot to get them to melt. And the boiling point is sort of ridiculously high for ionic compounds. The next is that they are electrolytes. That means is that we're talking about conduction. Okay? And conduction is always about the movement of charged particles. So when you're talking about the electricity in your house, then that's moving electrons. Okay? If you're talking about conduction in water, you're talking about ions carrying the charges. Okay? So whenever we're talking about conduction, we're talking about the movement of charged particles. So a solid ionic compound does it conduct? The answer is no. A solid ionic compound doesn't conduct because all of its charges are locked down in that positive, or in the three-dimensional matrix we're talking about. The charges can't move, so there's no conduction. But if it's a liquid or a gas, then those charges are now free to move, and it does conduct. Okay. But there's a third time that when ionic compounds are conductive, and that is when they are aqueous, okay, or dissolved. Okay. Ionic compounds like to dissolve in water, most of them, not all of them. And when they do, they conduct electricity. In that case, they're known as electrolytes. And finally, our salts, our ionic compounds, are brittle. And what brittle means is that when you squeeze them or hit them with something, they break. So the reason for that is, say, here is our ionic compound. Okay. Positive and negative charges, and we bring a hammer down on one spot and we hit it. Okay. We just apply a force. Okay. Then what's going to happen is that you'll see this. Where you hit it, you shifted the structure of the crystal. Okay. So now, where charges were being attracted to one another because they were of opposite charges, now they're being pushed apart by the exact same forces that used to be holding them together. Okay, so it's going to break. So, and it doesn't take very much. You only have to shift the structure of the crystal by, a single, ion. And ions are fairly small. So that is why ionic compounds are fairly uniformly brittle. Okay? Apply pressure or stress, then the crystal will break apart. Okay. So that is the ionic compound. That's how they're formed by, nonmetals taking electrons from metals, forming ions that are held together because opposite charges attract, non-directional bonds, high melting point, boiling point, forming an electrolyte that is to say, conducts in the liquid or gaseous form, or in the or when it's dissolved in water, and it is very brittle as a solid. Next up is covalent compounds. Covalent compounds, this is when you have two nonmetals coming together and they actually do share their electrons. They form an extremely local bond that is only between two atoms. Covalent compounds form the individual units known as molecules. Okay? Ionic compounds do not have molecules. Okay? Metallic compounds do not have molecules. Okay? So for an ionic compound, you see something like NaCl, that's just a ratio. Okay, there's one sodium, one chlorine. When you have, say, steel, which is a mixture of iron and carbon, it's like 96% iron, 4% carbon. It's still just a ratio. But carbon dioxide, you actually are talking about a single molecule, a thing. Where you have a carbon atom bound to two oxygen atoms. Okay. So these bonds are extremely local. The electrons are locked down in one spot. And the electrons are only shared between those two atoms. So this carbon is sharing electrons with an oxygen. It's also sharing electrons with these oxygens, with this oxygen over here, sorry. But these oxygens are not sharing any electrons. And now we'll put some eyebrows on there, maybe give him a chin dimple. And there's the face, and we've got a really weird looking dude. All right. All right. So because covalent compounds have these very local bonds, they have different properties from ionic compounds. Okay. The bond is directional, like I said. It's from one atom to another atom. They have very low melting point and boiling point because whereas your ionic compounds, they have these networks, that are held together by these, non-directional bonds. Okay. The molecular compounds, okay, the bonds are very, very strong, but there are no bonds in between the individual particles, or in between the molecules. So there are no intermolecular bonds. Okay, so this right here is a very strong bond, but the interactions between molecules are very, very weak. Okay, so they're not held together with a strong force, so their melting point and boiling point are very slow. Covalent compounds are non-conductive. Okay. The electrons, the charges are all locked down in those bonds. Okay, so charges aren't moving. So there's no conduction for our covalent compounds, and they are soft. Okay. You might think that ice is really, really hard, and you'd kind of be right there. But in this case, soft means that when you squeeze them, they can deform because the solids I should say, are held together by these non-bonding interactions, not by molecular bonds. So you squeeze them, you warp them, you twist them, and the result is that the individual molecules within can shift and realign, and instead of charges, you can think of them as like packed spheres or marbles or something. You can rearrange them fairly easily without actually breaking the structure. Again, water is going to be a weird covalent compound. Water is different from most of the rest of them. Okay. And finally, just to talk a little bit about metallic compounds, because I think they sort of complete the triangle there. Metallic compounds, you have two metals, or you could think of this also works for understanding a chunk of a pure element, a pure metal. They share electrons, but whereas our covalent compounds share it only between two atoms, a metallic compound shares it across the entire structure of the metal. It's sort of like communism. Okay. So what you get, as you can see over here on the right, is sort of like a sea of electrons. Okay, you have the metal atoms, the core of the metal atom, so the nucleus plus the core electrons, and then each one of those is embedded in a sea of electrons. The electrons are free to move around between the atoms. So once again, this metallic bond is non-directional. Okay. But they have a very high melting and boiling point because of that. Okay? So non-directional bonds means high melting and boiling point because it's sort of spread out. The bond is spread out across the entire structure of the metal. Understanding it's because of quantum mechanics, orbitals and so on, and mixing of orbitals, which we're not going to get into. But in order to break apart the metal, you have to break apart the bond. So still high melting and boiling points. And because you have this sea of electrons, the entire structure, the electrons are free to move from anywhere in the structure to anywhere else in the structure. So they are conductive. They're conductive whether they're solid or liquid. They don't dissolve in water, but they're still conductive. And they're malleable because even though it's a directional bond, a non-directional bond, excuse me, if you were to hit a metal with a hammer, then it's going to respond very differently from an ionic compound, because all that happens is, because these guys are all the same, and they're all perfectly happy, you hit it with a hammer, all you've done is you've shifted it down, but you haven't really changed anything. Okay? So everybody's still nice and happy. So that's why metals are malleable, meaning that you hit them with a hammer and they can be shaped, or ductile, which means you can stretch it out into a wire or whatever you want to call it. It's because all of these molecular or metallic cores are the same as one another within that sea of electrons. Whereas for ionic compounds, the ions are different from one another. So when you cause a small shift, then boom, it shatters apart. But the metal, they're all the same, so a small shift doesn't shatter them apart. So you can sort of sum that up in a table. So let's see, bonds are directional versus non-directional, boiling point, melting point, and conductivity, and response to hitting. Okay. So you have your ionic compound, which has a non-directional bond, has high melting and boiling points. That's 15 minutes. So let me turn off my timer really quick before it drives me insane. But let me just go ahead and finish this table. Conductivity, liquid or dissolved, and response to being hit is it shatters. It is brittle. Then you have your covalent compounds, which have directional bonds, low melting and boiling point, non-conductive, and soft. Finally, you have our metallic compounds, which again are non-directional, with high melting and boiling points. Yes, they are conductive, and they are malleable. Okay? They can be handled in that way. All right, and that does it for Lecture 2 of this, our second unit. I will see you again in Lecture 3.